Years ago, I actually studied, well, I studied many things, but I also studied water. But that time I studied water high up in the atmosphere, about 10 kilometers, between 10 and 25 kilometers. And that, of course, is quite far away from water in the urban context. It's still water. In the same way, the basic climate science may seem to be very far away when you deal with practical issues and practical matters of water in the urban context. And of course, you have many other constraints that you need to worry about. Laws, regulations, what's cost effective, what is not, other environmental aspects, and so on. But when it comes to climate change and climate adaptation, it of course is about how the conditions, how the temperature conditions, how precipitation conditions, how drought conditions, how storms and such like will change. And without that information, you can of course still do climate adaptation, but the risks are that you adapt to something else, and what is the likely or probable outcome for the future. Now, to tell everything between the heaven and earth and also in the oceans and so forth about climate in 20 or 30 minutes is quite a challenge. So you will get some highlights, and well, I hope that during the day will be time for discussions and so on. To begin with, climate science, of course, has a long history. We could go back to the 18th century when we started learning about, well, when our colleagues started learning about the greenhouse effect and the importance of greenhouse gas in the atmosphere, about the temperature and climate conditions on Earth. Over 100 years ago, Svante Arrhenius in Sweden made the first calculations on how the surface temperature of the Earth could look like if the atmospheric carbon dioxide concentration doubled. And he was pretty close to the right answer. And he was already at that time thinking about, well, we have started using coal and we add carbon dioxide into the atmosphere, and that will have an effect on climate. But what he also did, in addition, he got the oceans a bit wrong, is that he extrapolated and said, well, we may have doubled the atmospheric carbon dioxide concentration in maybe 3,000 years at the trends of his day. Now we are facing this within the next few decades in the worst case, but in any case during this century. The IPCC, the Intergovernmental Panel on Climate Change, which is part of the UN system, is maybe the most authoritative source of synthesis, assessment, information about the collected climate science. The IPCC assesses the physical climate system science about, well, how does climate change? Why does it change? What kind of climate conditions do we project for the future, the 2050s, the 2100s, and so on? And this in turn gives information, of course, to plan mitigation. What should we do if we want to avoid that the global mean temperature rises by 3 degrees or 4 degrees and so forth? What would we need to do in order to limit the global mean temperature rise to 2 degrees max? The IPCC also has a science on climate impacts, adaptation, and vulnerability. And the IPCC has science that is relevant to mitigation, which touches upon economic aspects about laws, other kinds of steering mechanisms. The basic messages from the fourth assessment report, or the AR4, as we say for short, from 2007, is that, yes, our climate is changing. The Earth has warmed up. And this is backed by a multitude of different science results, observations on temperature, on sea level, and so on. The second main conclusion is that, yes, it is because the emissions and greenhouse gases from the use of fossil fuels and land use change. Of course, there are some things that also are affected by natural climate forcing factors, but these are way too small to explain what we have observed today. The third one is that when climate changes, we get a higher temperature, higher sea level, precipitation patterns change, it will lead to impacts. In some regions, these will be more widespread and severe than others. In some regions, they will not be as severe. In some small regions, they may even provide opportunities for benefits, but not on the globe as a whole. We talk about impacts on water availability, agriculture, ecosystems, human health, infrastructure, and so on. And this, of course, leads to the motivation of the need of considering climate change mitigation, avoiding too large a change in the future, and adaptation, how to deal with the risks and limited opportunities that climate change will bring about it or bring with it, including in the urban water management context. I guess I don't need to preach here, because in Denmark and Copenhagen you have had ample reminders in the past 2 years about that the 100-year rain may come more often than that. And that in the independent findings that precipitation will, in a warming climate, become more intensive. Heavy rainfall will become more commonplace. What has been a 100-year event in some respects will in the future come much more often. If we make a calculation, or we sum the different temperature aspects up here, and start with the observed climate change, which in AR4 was this number 1.0 half a degree centigrade was until 1990 from the so-called pre-industrial era, the late 19th century. So that was the observed change. Then the climate scientists continued, and by means of physical climate system models that are based on the basic physical principles, thermodynamics, fluid mechanics, and so on, we made projections under different emission scenarios on how the global mean temperature would be expected to change towards 2100. And came up with a range that from 1990 to around 2100, the continued global mean temperature change would be somewhere just about 1 degree centigrade to more than 6 degrees centigrade. The sign is certain, but of course there's an interval, there's an uncertainty which seems quite huge. Well, large at least. In gross terms, one could say that half of that spread is because of we don't know how the future emissions will look like. And in these cases, these are non-mitigated futures, so there is no new climate policy assumptions. The socioeconomic drivers, population, technology development, are just something that would occur because of other reasons, other drivers. The other half of the interval is because of climate system uncertainties, which is much about the different feedback mechanisms. What happens when it gets warm? What happens to clouds? What happens to carbon cycle? What happens to, how the climate system enhances the primary effect of more greenhouse gas in the atmosphere. And the typical result is that it will enhance the carbon dioxide effect. Then there was a thought experiment which was continuing with models that if in 2100 the atmospheric concentrations of greenhouse gases that had been reached by that time would stay constant at that level, the climate system inertia, that it reacts somewhat slow to the forcing it's exposed to, there would be a further continued change in temperature, in precipitation patterns, and not least in the global sea level, about half a degree. Which means that in the non-mitigated futures, if there is no effective climate policy, taking into account the uncertainties in future socioeconomic developments, taking into account uncertainties in climate system science, climate sensitivity, the expected global mean temperature rise from the late 19th century would be somewhere between 2 degrees centigrade and 7 degrees centigrade. And yes, you may ask, well, 2 degrees, that doesn't sound so horrible. But in global mean terms, it is. One way of providing an example of what it actually means that if we consider, we can go back to 20,000 years. Well, Denmark was a bit more fortunate than Sweden, where there was more than a kilometer of ice over Sweden. It was the last glacial maximum of the last ice age, saying a bit sort of, not exactly precise scientific terms. And compare it to the past 10,000 years, when we have a naturally relatively mild period on Earth. So the estimated difference in global mean temperature between 1 kilometer ice of Scandinavia and today's rather good conditions was about 3 degrees centigrade. 2 degrees is not little. 7 degrees is huge. And certainly way past all the experiences we have from the past 100, 150 years, way, way beyond the information that you are probably using on temperature, precipitation, other factors when you plan infrastructures, when you manage water in the urban environment. The global mean temperature is an often used measure. In climate policy, one wants to limit the global mean temperature rise to at a maximum of less than 2 degrees centigrade. But when it comes to regional and local considerations, it is a bit deceiving measure because all the land regions, because of physical reasons, will warm up more than the Earth as a mean. Most of the ocean regions will warm up less. Especially large warming is projected for the Arctic region. And these regional patterns, of course, are important and relevant in addition to global mean values when one considering adaptation impacts, climate impacts and adaptation in places like Copenhagen or Denmark, well, Ørestad or Copenhagen or Denmark or the Nordic region or the Europe or, well, in different parts of the Earth. Now, this is a figure from the fourth assessment report from IPCC, and this combines a number of climate model results. The underlying socioeconomic and emission scenario is something one could call mid-range. It's not the worst, it's not the least, but it's an unmitigated scenario. And of course, if you ask me that what is a projected temperature rise, and I could give you this answer, you should be happy. Oh, I'm happy. Now I have a number. I can do that. Of course, life is not so simple, especially when you ask a scientist. Now we go to the Baltic Sea region. Now we have a number of result from a number of climate models, both global and regional, shown with different symbols. We have four different emission scenarios, A2, A1B, B2, B1, where emissions are larger in A2 than in B1 and the other ones are in between. What we are then looking at is that on the horizontal scale, we have the temperature rise projections, 0 being something they can call the present day, 1 degree rise, 2 degree rise, 3 degree rise, and so forth. And on the vertical axis, we have the projected precipitation change in percent, 10%, 20%, 30% compared to today's conditions. And as you can see, all the data points go towards the warmer conditions and towards more precipitation. Now, it looks pretty horrible. I mean, the direction is clear, but the magnitude of temperature rise and precipitation change is quite large, and of course, this can be conceived as or comprehended as being a bit complicated and difficult. Should you calculate for 2 degree rise or 4 degree rise? It may be an important factor for your decisions. Now, there is more information here. These data points point to the period 2011-2040. So the just started 30-year period. Climate scientists like to talk about 30-year periods because it's long enough to even out some natural variations within the climate system, but short enough so one can see ongoing changes over time. We have the next 30-year period, and we have the last 30-year period during this century. And one can see how the picture is of one of successive changes, continuing change. So we expect some changes during the next 30 years. We expect additional changes in the same direction in the next 30 years, and so on and so on and so on. And this brings a time aspect into the picture. Depending what you plan for, depending if you mind operations or new infrastructure, you need to think about different timescales and you need to consider different sizes of temperature change. Also, of course, minding the uncertainty, which, depending on the time scale, depending on the variable, you don't have to worry about this total time scale. The total range of results is more constrained than that. There's additional structure here. For example, if one looks at the colors, the A2 value is the highest emission scenario. In this case, point to larger changes, and the lowest emission scenario, B1 in this case, and so on and so on and so on. Now, it's about climate changing over time. Even though climate scientists maybe were thought to tell earlier about that we have one climate now and then we can tell you about the climate in 100 years' time. It's not that we go from one climate to the next, but we go from one climate to the next in a gliding scale also through successive changes. And one way of, again, trying to make this into a more illustrative example is to consider that if we, for example, would expect a 3-degree temperature rise during the next 100 years, the arrow on the map of Sweden shows where the gradient is 3 degrees centigrade between central and more northerly Sweden, and the temperature changes this much by over 500 kilometers. Now, if we take plus 3 degrees centigrade, that could occur over 100 years or during 876,000 hours, we get a speed of change which is about half a meter per hour. So, for example, if I were a pine tree or the city of Stockholm, I would be here today. Temperature rise that way. In 1/2 hour, I would be here. In 1/2 hour, I would be here. In 1/2 hour, I would be here. And so on and so on and so on. Half a meter per 1 hour over 100 years. It's not little. And well, now climate science has told us that what will happen if there's no new climate policy. There are uncertainties, but there are also things which are well established. In the international, European, and in the European Union member states, the ambition in climate policy is to limit the global mean temperature rise to at the maximum or less than 2 degrees centigrade compared to the pre-industrial. And as you could see from the other figures, other numbers that I showed, it is very, very, very unlikely that this can be achieved without ambitious climate policy. Do we make it? Maybe, maybe not. It's not certain. But we still have a shot at actually reaching that target. But even if 2-degree goal would be reached, it wouldn't mean that there wouldn't be changes. It wouldn't mean that the impacts would go away. It wouldn't mean that there would be no reason to consider the need of adaptation. You still do need to do the numbers and see if adaptation is something that you need to mind in your operations, in your decisions. It may not, but you need to do the numbers. Where are we headed then? Well, if you look at the past few decades, this is the global mean carbon dioxide emission curve, the occurred emissions, starting from 1990 and going, in this case, to 2011. And one can see that in the 1990s, the annual growth rate of global carbon dioxide emissions was about, well, roughly 1% per year. Since 2000, the number has been 3 times that much, about 3% per year, which is, again, a, well, regime change, one could say. In 2009, there was a small global decline. You know why that was. And of course, there was a decline in some countries, but there was a continued increase in some other countries. Since 2009, well, we are back with vengeance. 2010, the rate was almost 6% per year. And the first numbers for 2011 point to around 3% per year, so we are back on the curve, unfortunately. In order to reach a 2-degree goal, the global mean emissions should culminate as soon as possible, stop rising, and they should be more than halved by 2050. In industrialized countries, they should pretty much be diminished or reduced by 85–90%. So goes the thinking. And in these trend patterns, we are not going in that direction as yet. About half of the carbon dioxide emissions that come to the atmosphere from the emission of fossil fuels and land use change go back into the climate system in the global ocean and terrestrial ecosystems, the carbon sinks. The other half accumulates in the atmosphere. And the growth rate in the atmosphere has increased decadal rates 1.3 to 1.6 to 1.5 to 1.9 parts per million or micromole per mole per year, which you would expect because the carbon sinks are not picking up speed. They are not becoming more efficient. What if anything, they are expected to become less efficient in the future because of climate change. So the growth there is increasing. We are adding faster greenhouse gases into the atmosphere as we speak. And the global mean temperature has risen, of course, not only over the 20th century, but not least during the past decades. The warmest year in the observed temperature series is, anyone? 2010. Then we had 2005. Then we had 1998. 2011 was about the 10th or 11th warmest year. But the blue bar show you years when the global mean temperature is expected to be cooler than in the mean because of large-scale natural internal climate system variations, so-called El Niño, La Niña variations. And it happened to be the warmest, naturally cooler year so far. You can also see that there's natural variability, which is due to things within the climate system. It's not about the amount of carbon dioxide suddenly becoming less and suddenly more. This is totally things going on between the atmosphere and the ocean. The global mean temperature, as is talked, it's the global mean surface temperature in the air. Whereas the atmosphere and the global ocean exchange large amounts of heat with one another. And in one year, there's some heat going from the atmosphere to the ocean. The other year, the ocean is giving back in the atmosphere. So it's the long-term trend that evens out those differences. The annual variations in the global mean, well, they are even larger, of course, in the regional sense. We don't have to go back very far, and we find quite a cold winter, which was not the coldest ever. We don't have to go very far back either when we find the warmest year, these parts of Scandinavia. 2006 or thereabouts, the eastern Sweden had its warmest or mildest winter ever during the past 100, 150 or maybe 250 years. The past 20 years of climate data, annual precipitation in Sweden, compared to the previous 30 years, 1961, 1990, give evidence that the annual mean temperature in Sweden has risen more than 1 degree centigrade, more than the global mean. And there has also been an increase in precipitation around, well, up to 10%, around 10% or so. And this fits well, this is well in line with the global mean temperature change, even though, of course, there are also internal variations, natural variations, not least in the local and regional scale playing in. What news today? The IPCC will come with its 5th assessment report in 2013-2014. I happen to be one of the authors. We are quite a few. But we are compiling the collective published climate science again as we speak. I'm a bit stressed because we need to respond to all the expert comments for the previous draft and write a new draft by the end of July, which will then again go to expert review. And actually, I can't tell you what will be there. We are not done yet. But what is there is based on published literature. Not least scientific articles, but in some cases there is also use made of technical reports. The EA reports, for example, would qualify as technical reports, or the World Bank literature would qualify as technical reports, but predominantly from the peer-reviewed scientific literature. Since AR4, there's a so-called cutoff date when one stops reading new articles so that the assessment can still be made. The cutoff date for AR4 was 2006, which means that since 2006 we have 6+ years of exciting new science. We talk about tens of thousands and tens of thousands of new results, new scientific articles, and so on and so on and so on. Nevertheless, it's I do dare to wager that the basic findings will not change. The Earth will still be warming up. it will still be because of us. We are still facing a significant future change, not least if we don't do anything more ambitious that we have done so far. There will be a lot of new results and other new details, and some of these may matter. There are new results about regional scenarios, there's new information about extremes, there are new results about feedback, and so on and so on and so on. So it will be worth reading and considering. One of the novelties is that the underlying socioeconomic assumptions and scenarios will be different from AR4. They go under the names of RCP, representative concentration pathways, and SSP, shared socioeconomic pathways. And they will be put through a new generation of climate models within the so-called CMI5 project. So there will be new information which hopefully will also lead to more and improved impact analysis and means of planning what to do. Another novelty is that whereas in AR4 the climate projections were done for the climate change. You could say climate change over time, or mean climate change, how mean temperature will change, and so on. And they address the 21st century. In AR5, there will be a new class of climate model simulations which can be put under name climate prediction or decadal prediction, where the timescale is shorter, up to 2030s or so, but where the intention is to try, in addition to the forced climate change signal, to capture the interannual internal climate system variability. For example, when will these naturally cooler years, the blue bars you saw earlier, the naturally warm years, the reddish bars you saw earlier, occur? This may or may not succeed. It's very much in the scientific domain. What this matters, of course, is that depending what we consider in the society, different things are relevant in different timescales. So here you have the operational timescales, for example. Here you have when you plan new major urban infrastructure. Here you might have additional things and so forth. So again, there are more starting points to do these considerations depending on what you do. There are some new results from the IPCC already. There have been new two special reports, one about renewable energy sources, came out last year, and there's a special report about extreme weather events put in a disaster risk and disaster management concept. And these you can pick up from the IPCC website and you can read them. And these contain science which is newer than the AR4. The special report on extreme events, or the SREX, it confirms by and large the AR4 findings on extreme events. We can expect more warm events, less cold extremes, changes in heavy rainfall and drought. Changes in storms are still uncertain and perhaps, not least for the tropical hurricanes and typhoons, more uncertain than earlier. There are complications. They do not need to change. More damages and losses, which of course is a combined effect of consequences of changes in extremes and changes in the society, how we build and manage the systems. Climate change will, and that's observed, climate change will lead to further changes in these, in many cases in the same direction as what we already have observed. And of course, how the impacts then turn out to be is very much connected to how the society develops, how we plan, how we build, how we operate different systems. And this actually, going back to the heavy rainfall in Copenhagen, that extremes of course occur when the ambient large-scale atmospheric climate conditions which are favorable to extremes to appear change, and the latter change with time. So the risk with different kinds of extremes changes before the extremes actually are on us. So even a starting temperature change and so forth, it will change the risks of heavy rainfall, very warm days, high sea level episodes and so forth. Well, finally, should you wait for the AR5 before you do anything? Final slide. I mean, come on, we have 20,000 new articles and we have hundreds of scientists who are compiling, assessing this, and the models are better and all that. Should we wait? Well, no, I don't think so. The basic findings are there. And, well, you can leave it to scientists to do new scenarios and do the new assessment, and then you can take it and read it. It will be interesting. But of course, what you also need to mind, and this you know much better than I, is to know your systems. Where are the vulnerabilities? What are the conditions under you operate? What is the EU policy? What is the national policy? What the action is across the societal part, regional, local, private action, public action. And of course, one considers legal aspects and insurance and responsibility and earnings and so forth. So climate information is relevant in climate adaptation, of course. But I'm, even as a climate scientist, very aware of that it's not the only constraint or the only factor that one needs to mind. Thus, you have my full respect in dealing with this in your own responsibility. I couldn't do it. Thank you.